Hello everyone, welcome to the last technical paper session of the day, which is going to be about simplification and compression. We are going to have two talks. The first one is from Yusuf, if you want to set up the computer. The title of the talk is a partition-based method for spectrum preserving mesh simplification. Yusuf is a professor in the computer engineering department in the Middle East Technical University in Turkey, working broadly on geometry processing, and today is going to tell us something about simplification.
Hi, I am Yusuf Sahillioglu, and this work with my something. Some technical problems. I can't see anything here, that's why. My opening cloak is also ruined. Pretend that you don't see it. It is about the musician size of Justin and me. But it is relevant, don't worry. Yes, I am Yusuf Sahillioglu, and this work with my master student Misranur Yazgan is titled A Partition-Based Method for Spectrum Preserving Mesh Simplification. I will present it now. We can reconstruct the length of a string from its sound, as hinted by Justin's Laplace lecture. We cannot, however, reconstruct a higher dimensional entity, like the shape of a drum, from its sound. Although a perfect reconstruction is not available, we can still learn quite a bit about the shape of an object from its vibration modes and frequencies. And this is where the mighty Laplacian comes in, as its eigenfunctions and eigenvalues enable us to look at these modes and frequencies when we tap it with a hammer. Being that much informative, it makes so since it is informative, it appears almost everywhere in geometry processing application, and that's why it makes sense to work on a project that protects it. And let me give our motivation more properly. Since the eigenfunctions of the original model and the low resolution simplified model are not consistent, especially for high frequencies like the axis here, the related computations that are carried out on these low-resolution meshes could be misleading. Same goes for the eigenvalues, as they are also mostly inconsistent. So if we can somehow achieve consistency, then all these important geometry applications will be happy, and more formally, it will be accelerated by enabling consistent computations on low resolution. So these applications range from feature extraction to distance computation, for instance. And if we take shape correspondence task, the revolutionary functional maps are efficiently represented by the orthonormal eigenbases extracted from the Laplacian. And working on simplified models is faster, like 10 times faster. But only makes sense if the simplified models Laplacians hold the spectral properties of the originals. So this is just one motivational example I stole from this paper. I have also my own examples in the results section later. So it is customary to call the Laplace-Beltrami operator as a Laplacian, which basically encodes deviation of a point from its neighbors. And by doing so, it links geometry of manifold to the heat flow. We have symmetric uniform Laplacian as well as the geometry-aware version, cotangent, which is still symmetric. And Laplacian spectrum is defined by its eigenvalues, lambda, and eigenfunctions or eigenvectors, phi. And Laplacian is symmetric positive definite, so its eigenvectors, eigenfunctions, define a proper good orthonormal basis. We can make it even more geometry aware by injecting the mass or area matrix to the mix like this, and when we multiply both sides by A, we end up with this so-called eigenvalue, generalized eigenvalue problem, which takes two matrices, L and A, not just L. And this is the behavior of eigenfunctions corresponding to different eigenvalues or frequencies. As you can see, first vectors, functions towards the left, they change slowly, smooth, they are smooth, whereas the last ones have rapid oscillations. The very first one, the leftmost one, in fact, it does not change at all. It is extremely smooth, it is constant, so it is useless actually. We typically drop it. So let's see the related work on mesh simplification. They come in two flavors, appearance-preserving and spectrum-preserving ones. The prominent example for the former is this quadric paper, which assigns echoes to each edge and puts them to a priority queue and extract them from there and collapse the edge is based on that order. And the cost is basically sum of squared distances to the supporting planes of the edges endpoints. Recently, Liu et al. Presented the intrinsic version of it, which is focusing more on equation solving on surfaces, not surface display. And here are even more related papers, spectrum preserving ones. So this cool energy function, they use it to end up with a quiescent operator, not a quiescent mesh. So this is important. They don't produce a mesh. They produce the quiescent simplified operator by minimizing this commutative function. So what it does is they define some function phi and they apply the operator and then they project it to the simplified domain. And the other path is they first project the function to the simplified domain and then in there they apply the simplified operator. And if these two paths give same or similar results, then it means that these two operators share similar spectral properties, so they are good. And they minimize it. The first one does some Galerkin formulation, and the second one uses chordal solver. Another paper uses the very same energy, but not globally for the entire operator. They make it local per edge, which enables them to simplify the mesh by edge collapses, just like we do. And they produce a mesh, again, just like we do. So basically, this is the closest work to our case. Recently, we also see this generalized spectral coarsening action, which uses multiple Laplacians. So we need a series of edge collapse operations to perform the simplification. So we take an edge with two endpoints, U and V, and we basically put U on top of V, then relocate it somewhere. And the inverse of this operation is called vertex split. As far as the implementation details go, it is obvious that one vertex is removed, the red one, and also two triangles, they just shrink to zero area. And it is again obvious that we remove one edge, the victim edge E. But I highlight that these two edges should also be removed because once you do the collapsing, they collide with the black edges on the left. So you shouldn't keep duplicates in your programs to avoid agonizing debugging processes. So I kindly invite you to remove those two as well. And so now let's get to the method. We directly consider the eigenvalues for the first time in literature for this task. And we only use the smallest k eigenvalues, k typically being 15. We do so because high frequency components will not be present on the quiescent mesh anyway. And the idea is we collapse a single edge, end up with a new mesh, compute its eigenvalues, and compare it with the fixed original eigenvalues. So we plug this norm into a framework like this, which goes through each edge and collapses it and takes the norm and assigns that cost to the edge, and then undoes the collapse with the vertex split to start from scratch. There is this if condition. Some edge collapses are not legal or successful because they lead to like sudden normal flips or foldovers, so we should avoid them. Just an unnecessary, actually necessary detail, but not very crucial. So the crucial point is this is slow, intractable. We cannot do this actually in practice because we have like hundred thousands of edges, and this requires making some eigen decomposition. So we will introduce some solutions to make it doable. First solution is partitioning. The mesh is divided into smaller partitions, and each partition is simplified separately. So instead of dealing with one huge Laplacian for the entire mesh, we basically have Laplacians per partition. And naturally, we now have faster eigenvalue decompositions, and also additionally, we have fewer edges to consider, like to select the lowest cost one. We will look at fewer edges now. And the main downfall of this approach is this edge cut regions staying between two partitions, like the light part here, and also the purple part in the bunny. So it is not the end of the world to have these regions, because after all, they will be indirectly simplified. As you can see here, whenever I collapse an edge on the boundary of a partition, a triangle in the region will also go away, like 4 light green triangles. I now have 3 of them. So they will not stay in the original resolution, which is a good thing. But again, we don't have direct control on these regions. That's why we want to minimize these regions. And to do so, we use this Metis partitioning tool for our partitions. Basically, it has this option to prioritize minimizing edge cut regions, specifically the number of edges in these regions. And while it does so while keeping the partition sizes balanced, it guarantees each edge belongs to only one partition so that partitions don't affect each other. And now for a proper spectrum preservation, number of vertices in each partition on the output mesh should be at least 3 times k, as demonstrated experimentally by the previous work. So this fact bounds the number of vertices that can be removed, because I shouldn't go below 3k for each partition. And it may be annoying or bad because I may not reach my desired level. So we propose this solution, multi-step simplification with hierarchical partitioning, that I will clarify now with an example. Assume that your input is a 25k vertex mesh, and I want to go to a 2k vertex mesh with 100 partitions and k equal to 15. So by the 3k rule, we can put we shouldn't put less than 3 times 15, 45 vertices to each partition. If we go below that, then spectrum preservation will not be proper. So we have 45 vertices in each partition at the minimum. We have hundreds of them, which means I will end up with a 4.5k vertex in the end, which is higher than my target resolution. So what I do is, I now take this simplified model and use less number of partitions on that model. Less number of partitions imply larger partition sizes, which is not a big problem here because I am currently not working with a big model. I got rid of my 25k model anyway, so I am working with this simplified model now. So big partitions, I don't really mind them at this point. And with like 50 partitions, again, 45 per partition, if you multiply these two numbers, you get close to 2,000. And then you do it again to hit 2,000. So to wrap up this important part, you need to look the figure from right to left for the partitioning idea, because we have this binary tree structure. Like I take this partition and divide it into 2 to obtain the binary tree structure. But the simplification goes from left to right in fact, as I just described, first 100, then 50, and so on. Another solution is what we call similar edge elimination. So we similar edge term stands for the edges whose removal affects the spectrum as close as possible to each other. We normally look at all the edges and collapse low cost edge, one edge. But now we want to consider n edges, not just the lowest one. However, collapsing these n edges successively without any control may not be good for spectrum preservation. So what we do is, for the upcoming x steps, we select the best edge among the n edges only. So in other words, we consider all edges in the partition every x steps, and for the remaining steps, we just consider n edges. And typically n20 and steps x4, here I highlight those 20 edges in this partition. And last but not least trick is the threading, maybe the most important thing actually. So we have these each partitions, they will be simplified separately. So we are ready to parallelize them. So each thread can run a partition. However, there is this race condition business, as we know, running all partitions at once may cause race conditions. Let me give you a quick example here. If I collapse this edge on this boundary of partition P2, then this vertex used by this pink triangle will be updated. Its index will be updated. So if I try to simultaneously collapse the pink edge here, there will be a confusion. So I should take care of that. I can take care of that using mutexes or other synchronization control mechanisms, but they will overcomplicate my system. So what we do is we do this. Only run partitions concurrently if they are not direct neighbors. And this action calls for the graph coloring problem, since we are talking about direct neighbors and so on. So basically, I create this new graph with vertices being partitions, and if they are neighbor, then they should get different colors. So in the end, I end up with these batches, and I run threads or equivalently partitions batch by batch. So for example, I first do the purple batch in parallel, then I do the red batch concurrently, and so on. And graph coloring, we pick a greedy algorithm to handle that. Basically, given an order of vertices, we put the next lowell is not a word, next low legal color to that vertex. Like here, V1 gets the first color, color 1. Then in this order, V7, it cannot get color 1 because it's not legal, they are neighbors. So we give it color 2 and so on. So here is the complete algorithm then that depends on 5 parameters I discussed. And basically, we process batches sequentially, and given a batch, we process all its threads in parallel. That is the main idea. And I can go through the results for the remaining minutes. So as the partition size increases, naturally the corresponding Laplacian for that partition increases, which leads to slower eigen decomposition and slower execution time. And as partition size increases, accuracy also increases because now each partition represents the overall neighborhood better. As the number of eigenvalues to protect, explicitly protect, increases, again, naturally, eigen decomposition increases. But on a related note, we observe that after some point, accuracy does not increase any further, so it is enough to protect eigenvalues explicitly to a certain extent. Threading. So if you use only one thread, main thread, in other words, you don't use multi-threading, then we have terribly slow times actually. But as the number of partitions aka threads increases, then timing decreases. However, I should note that since not all threads run concurrently due to our race condition prevention, there is no linear relationship between the number of threads and the amount of acceleration. For instance, if there are 100 partitions, we get this average number of threads per batch. This number is about 30. So what this means is I can literally run 30 threads in parallel, but on a typical PC, like a single PC with 4 cores, since I don't explicitly have 30 CPUs cores around, I do this interleaving and context switches. So in this example, I need to do about 7 passes to use the existing cores. So if I literally provide 30 cores or more, then this will have a speed up. So, and this is where we employ the 6-node cluster of our department, and we observe speed up for the models that really do use a lot of concurrent threads. For instance, for the bunny model, apparently we don't use that much threads, so it is not improved, but others improved. So this final row, this final row represents our timings. And as far as the comparison with the literature goes, the last 2 papers here, they coarsen the operator, so they don't produce a mesh. They basically sample points, and they that will live on the simplified domain, and they display that samples. The Lescott et al. On the other end do produce an output mesh, and it is here, and this is ours. So the quantitative evaluation is like the functional map matrix. The closer that matrix to diagonal, the better the preservation is. And similarly, these 2 norms, the closer they are to 0, the better the preservation is. So on a different example, we see our advantage, for instance, and the general conclusion I will give in the very end. But for eigenvalue direct comparisons, like literally we compare the eigenvalues with the reference actual original 100 eigenvalues versus the other methods productions. As you can see, even though we explicitly preserve the first 15 eigenvalues, the trend is we get aligned, we keep aligned with the 100 other values, so that's good news. And this is just another view to this comparison. Actually, we take the L2 difference between our 100 values versus the ground truth 100 values, and our difference blue is smaller. And for a surface area preservation application, for which only Lescott is eligible, because the others do not produce a surface mesh. So we are close, like they are both able to preserve surface area. And we do this comparison because Laplacian eigenvalues are related to surface area actually. There is a formula that lets you derive the surface area from eigenvalues. But actually that requires a very high resolution mesh, which defeats the purpose here. So I don't use that thing here. I just, inspired from that, I just show surface areas. Maybe more legal applications are the following. Like the first one is preserving using eigenvalues only, the shape DNA descriptor. Here is the 2D MDS multidimensional scaling embedding of the models based on these descriptor distances. So the spheres represent the original models embeddings, whereas the cylinders represent our simplified versions embeddings. They are close to each other, which is a good thing. And here is a set of applications, spectral applications using eigenvectors only. this one is spectral clustering. It is using the second smallest eigenvalue, eigenfunction, the Fiedler vector, to make this partitioning, as you might know. The middle one is our result. The leftmost one is the original non-simplified model's result. And the rightmost one is the Lescott result. We have the same format in the other triplets. The bottom left triplet is about Laplacian eigenmap. We basically use the first three dimensions, entries, to get this embedding. This is a better embedding method called Laplacian embedding. Basically, we project the coordinates to the subspace spanned by 30 or 100 eigenfunctions. And again, our projection is similar to the original projections on the left. And finally, so we did eigenvalues only, eigenvectors only, so why not just find applications that are using both of them at once. And for that, we can use biharmonic distance, heat kernel signature, the runner-up for the test of time award, and also some sampling action. As you can see, the leftmost, or the top here, belongs to the original resolution, and the other is computed on our simplified models with our eigenvalues and function vectors. And yeah, so in conclusion, this is the first spectrum-preserving mesh simplification method, which is considering the eigenvalues directly. So there are other methods around, but this is the eigenvalue consideration, direct consideration is the first thing. So we believe that this method will benefit the future work built around the eigenvalues. More concrete future work directions are like further acceleration or further accuracy using different remeshing actions. And so for the comparisons, we outperform the other three methods around for or indirect. So it's not indirect, of course. So for direct eigenvalue comparisons, also we outperform them in this under this norm, which uses eigenvectors and values at once together. Chen et al. Is best for the functional maps comparisons where eigenvectors are only used, and Lescott et al. Is always the fastest. Yes, so with that, I will stop. This is Misranur, my grad student who couldn't come, and I am Yusuf.
Questions? I'll start with one. So how, like, does it look, the result of a simplification, does it look very different than, let's say, Q-slim? And can you say something like, is there some geometric intuition of what preserving the spectrum means?
Yeah. Thanks for bringing that up. I put the slim result actually to the very beginning before my joke. So the right-hand side here is the Q-slim, by the way. The middle one is ours, and this is the original. So although we don't do anything directly about appearance, apparently this preservation, also spectrum preservation also helps with that. This is mainly because the eigenvalues relation to surface area, in my opinion. I don't have a valid theory behind that, but so it, for instance, another example is here, again, I didn't emphasize, but now that you brought it up, so in this application, if you look at the cuboid here, the gray one, it has a lot of sharp turns, crease, edges, and they are also preserved by just preserving the spectrum. So spectrum preservation helps with that, but yeah, I don't have a qualitative comparison like difference of appearances.
Okay. Any question from the audience? We are running a bit late, but we have time for one more quick question. microphone there.
Hi, thanks for the nice talk. I'm not sure, maybe you answered it already, but you said you're using 15 eigenvalues, right? Did you play
15.
around? 15, didn't you say 15?
15 eigenvalues, 1, 5. Are you talking about number of eigenvalues I preserve?
You said you're using the first 15 eigenvalues?
Yeah, first 15.
Yes, yes.
Yes.
Did you play around with that? Like, did you try what happens if you use like 5 or 20 or 100? Does it? Did you try that?
Yeah, we did actually. So 15 seems to be a good compromise between accuracy and time. Actually, according to these norms, 30 seems to be a good accuracy level, and after 30, we actually see the accuracy going down by this action. But with 30, it is really slow. Like it doesn't grow linearly. The eigen decomposition is cubic, has cubic complexity, like close to cubic. Actually, it depends on matrix multiplication implementation. So the trade-off, we ended up with 15, but below 15 is not accurate at all. So yeah, empirically, we picked 15.
Thanks.
Thank you again. Thank you again.
Yes.
So the second talk is entropy-driven progressive compression of 3D point clouds, and the talk is going to be given by Armand, which is a PhD student at INRIA Sophie Antipolis in France, and his work is about making possible in the future to stream and interact with massive point clouds remotely.
Well, thank you, Daniel, for the presentation. So I'm going to present entropy-driven progressive compression for 3D point cloud. And I'm going to start by giving a bit of context of why we are interested into compressing point cloud, a very brief context, explaining how we can approach the problem, and then presenting our method of compressing 3D point cloud compression. So to present the context, we are working on digital twin, and the problematic of digital twin is like we have a lot of industries which is pretty old, and the maintenance tasks are pretty costly. And for that, we generate duplication of the site with point cloud and adding information for collaboration on a point cloud and on an industrial site. This kind of application allows to accelerate multiple tasks, mainly maintenance, trainings, contracting, and so on. And it works in this way. We have a 3D platform on which different actors on the ground or elsewhere can interact. To make this 3D platform work, the one we see on the left here, on the right here for you, we stream a 3D point cloud on a network. And the problem is the 3D point cloud is a very heavy object. So we need to find tricks to be able to visualize it even with low dB rate of data. So our project is working this way. We start from a 3D point cloud, here geometry of 3D point cloud, and we try to generate a bit stream, so a series of data, of integer, that allow to reconstruct the point cloud at different level of detail. Our final objective is to optimize the curve that we see here on the right, which is a rate distortion curve. So it presents on the y-axis the rate, the distortion higher is better, and on the x-axis is the rate of data. So more on the right, and the more data you send. And the objective is to send almost no data and still be able to reconstruct the point cloud. So state-of-the-art present two main family of solutions for point cloud compression, which are assembled in the family of in standards. So the first one is GPCC, which works on octrees structure, and the aim is to give details of the point cloud based on the octree decomposition. And the others with GPCC Plano and VPCC are working on 2D projection. So you find planar surface on the 3D point cloud, and using those planar surface, you reduce the dimensionality of the problem from 3 dimension to 2 dimension, and you can only work with the buffer maps. I will now present my solution, which is similar to the first family, and I will explain how the first family is compressing data first. So to do so, I will give a very brief explanation about quantization that you might know, but it's just for the context. So if you want to represent the value 5 with 3 bits, how do you do so? You first decompose the interval into 2. So here, 5 is in the right. Then you do the same thing on the sub-problem, and you do it iteratively. What is interesting is each time you say, I'm on the right, I'm on the left, I give more detail, but I have already a good approximation with few most significant bits of this information. Another observation is when you work with a quad tree, octree, tree, or odd tree in higher dimension, it is the exact same data structure, just in higher dimension. So here, we have 1 bit of data for each dimension, and we can go higher with having 2 bits of data for higher dimension. So this was used in a different method, and here we present de Villers-Gandouin, which was proposed for point cloud compression. And how the method is working is similar to octree, but here only with binary space partition. So we start with a point cloud, which is contained in a box, and we just send the header, which is a box where it's in, and the number of points, so if 32. We then choose the longest dimension of the point cloud, so here, for example, the x dimension, and bisect it in 2. When we bisect it in 2, we will have on the left side a number of points, which we add to the bit stream, and the number of points on the right will be automatically deduced from the mother cell number of points. An interesting point is on the left, we have, for all the 16 points that are on the left side, we have encoded 1 bit of information for the x dimension. So we are encoded only by saying 16 points on the left, 16 bit of equivalent. And the higher the number of points, of course, the higher the number of bits. We then iterate on this and subdivide each time the longest dimension, which allow to produce at each sequence an additional bit information. So this is a standard method. And we present a method which is another approach to the same problem. So we start with the same kind of problematic, so the bounding box and the number of points, but instead of deducing the plane of bisection, we just introduce one manually. So here, we select a point. The problematic here is we cannot just send the number of points on one side, because we also have to provide the information of which plane we used to bisect the cell. And we do it iteratively. So here we start with one cell, we do the same thing with the other, transmit the second plane and the number of points on one side, and do it until we can reach the final level of detail that we target. Comparing the two methods, we can see that one of the problematics we have here, we have to send the number of points. An interesting observation is also, oh, sorry for that. Well, it should be a bit sweet, but sorry. We don't have really the position of point when we send this. We just have cells with a density of points inside. So some kind of color which represent the number of points in a cell, which is not very accurate, but allow to reconstruct the point cloud at the end level. This is a representation of the tree that we get. One observation is our method give a bit of a longer tree, which will be very important for later remark. So why are we interested into doing a bisection with a plane that we propose? Is if you observe such a case, with a standard approach, you would have to do 72 subdivisions on the left, while our approach will only give 4 subdivisions to get a level of detail which is approximately similar. So the question is it worth it to send 4 planes, to have to encode 4 planes, to just get this level of precision and don't have to send intermediate information? So those kind of encoded methods are called transform coding. Those are very, very common for compression. And to present basically the idea is we present a point cloud which is on a high dimensional object, but often have a low dimensional structure. The idea of a transform coding is to find this kind of transform that allow to simplify the point cloud and find some kind of structure that we can leverage to then encode more easily. So here, if, for example, we only have a simple transformation, which is a rotation, and we end up with a two-dimensional object instead of a three-dimensional object. There exist many different types of transform coders. So the orthogonal approach, so that you might know, mainly Fourier, that is very famous, of course. Non-orthogonal with neural network, which don't maintain the orthogonality parameter. Linear and non-linear. Our method will be in the locally orthogonal family of method and a non-linear approach, since we are iterative and it's a level of detail. So about optimization, the first thing is we want to find a plane that optimize our ray distortion. And to do so, we have to define what is an optimal plane. For that, we will first introduce the entropy. So entropy is defined with this formula, very simple formula. And it allows to give you, from a sequence of codes, the number of bits you need to encode each one. So here, for example, we have 8 values, and for which we need 3 bits to encode it. So 2 to the power 3 give 8, and that allows to encode all the data. If we get another distribution probability, so here we always have 3 instead of anything else. And we do the same calculus, we will find 0, which is logical because you always know that we get a 3 as the next symbol. So you don't need to encode anything, it will be a 3. And if you take another distribution, so for example this one, you will get something between 0 and 3 for this case, here it is 2.25. And an interesting observation that was used for compression is you can leverage this information. You can use a method, a transform, which allows to give shorter codes for things that are very recurrent and longer ones for elements that appear pretty rarely. So here, if you check the value 2, it appears 50% of the time, and it has the shorter code because it's the higher in the tree, while 6, which appear pretty rarely, is the lower. This allows to approximate the entropy we defined earlier and can be used for point cloud. But one of the questions is how can we define entropy for a point cloud? Because for a sequence of symbols, it's well defined, but for a point cloud, it's a discrete distribution. We don't have repetition of points because that's of no interest. And what we can say is, intuitively, if we had a dense point cloud, with points that are well localized, we will have a low entropy because everything is pretty much in the same place and have some structure. Similarly, if you have something pretty random, we will have a high entropy because nothing is predictable. And the transform that we should use to optimize this should allow to do the two things: localize point and densify the density probability of point. The problem remains of choosing the best bisection surface. So if I give you this kind of point cloud, and I ask you what is the best bisection surface, it's an ill-posed problem. But we can define 3 parameters that we identify that are interesting for point cloud compression. The first one is carving empty space. So when we have a point cloud like this, if we choose this bisector, it allows to remove a lot of empty space, and so we know that we don't have any points there, and it brings information and will allow compression. A second interesting idea is to separate objects. When you have a lot of objects, we want just to separate them because then we can do additional carving, which allow again to gain on the red distortion curve. Lastly, when we are in the case where we don't have an optimal section, like very dense cell, we just want to bisect it in a way to give more details on each side. And the question is how to find a metric that allows to optimize those 3 kind of operations. For that, we define the entropy-based plane optimization. So starting from the point cloud that we saw before, we just diffuse a ball around each point. So here we see in light blue the diffusion function. And when we want to evaluate a plane, so in yellow here, we define few volumes. Here we have V1V, which is the volume of empty space on the first cell, and V2V is the volume of empty space on the second cell. V2F will be the volume of full cell, so the volume in blue, of the second cell. And we will define the entropy on this element. So we will define the entropy of full space and empty space. So to do that, we define different ratio for each cell. So here, the ratio of empty space into the first cell, which is 1 here because we don't have full space. Then we use this empty space and this full space to define the ratio of full and empty space onto the second cell. We then define this formula, which has 4 parts, and each part is an entropy metric of one of the parts. So here is the entropy metric of the empty region of the cell 1, and the last one is the entropy of the second cell of the full space. We give now an example of the plane optimization that this metric can achieve. So here we can see we start by bisecting the point cloud, optimizing the density of the upper cell. Then we do the same thing, finding a straight line in the middle. Then we have the opportunity to remove empty space on one side and on the other side. Lastly, we find this plane which removes also empty space. This one which bisects the space. This one which also allows to remove a part of empty space. This bisects the space, and we continue until we have some level of details that is targeted. An interesting remark is we still don't have the point position. We just have the density information, so we have this information. We know a cell, its geometry, and the number of points inside. Speaking of quantization, we introduced the bit stream like this. We say we start by giving the bounding box and the number of points. And we give a set of planes. So the first plane that subdivides the cell, and the number of points on one side, the second plane, and so on. But to transmit this plane, we have to do some additional information. So we decompose the plane into 2 information, which is the normal to the plane, and its displacement to origin. So taking the standard equation of a plane, the normal is simply defined as the ABC term, and the distance to origin is simply d. With that, and if we consider that N1, which is a 2-dimensional object, which is its sample on S2, we can generate a bit stream that we can then arithmetically encode. To represent the normal direction and to represent a 1-dimensional element, we use a Fibonacci sampling. To introduce it simply, we roll a curve around the sphere, and we will simply just regularly sample it, which allow to give a set of points which are sampled on S2 and which are pretty regular on the sphere. Advantage of this method is that we can sample arbitrary number of points. We can just increase or decrease this number, and it will be useful later for some optimization. Because one of the observations we have is if we transmit the plane with the full number of bits each time, we might pay a lot, especially at the end time, because when we don't have an optimal plane, it's not very interesting to give a lot of information of how the plane is in space. So instead, we adapt the number of bits we will spend to encode the plane, depending on the cell structure. Few observation was when we have an high precision in the plane that bisects the space, we'll have an accurate geometry because the plane can be well represented. But if you have high precision, we also have high bit rate because we have a lot of planes that are candidate to bisect the space. And the last observation is when we have a cell which is pretty dense and have localized point, we don't have an optimal bisector. It's not any bisector will do the job. So this is why adapting the quantization is interesting in this case, because we can reduce the number of bits that we spend on the plane with that. So to do this adaptative quantization, we first want to estimate the cell dimension. Remember, the cells are convex 3D objects in space. To first estimate the dimension, we do a 3D triangulation of the 3D cell. We then calculate the PCA eigenvalue of the cell volume, which is defined in closed form for a convex cell. And we can estimate each dimension of this cell with the following parameter. Simply put, it represents a box, the PCA of a box, and it gives the dimension from that. This estimation will be used for direction quantization. First thing we do is we estimate the dimension of the curve. As you might imagine, sometimes we can have a cell which is planar. If we just put one plane on top and one plane on the bottom, we'll just have a plane, and it's not very interesting to spend a lot of bit to have a lot of direction in that. Similarly, if you have a pen, like a very linear kind of cell, every dimension is approximately equivalent, so it's not useful to spend bits. So we estimate the dimension with this formula, and we define the number of quantization we want, the number of candidate plane direction we will have with the following formula, which adapts to the cell geometry. Yep. So to give the result, we also use the moment adaptative based sampling. And what we observe is when the cell is 3D shaped, we have a sampling which is in all directions. When it's 2D, we sample on one main direction, which is the direction which are in the direction of the plane. And when we have a linear cell, we only sample one direction. So we don't actually need to spend anything for this because we know which direction it is. For displacement, because remember we have the orientation of the plane, but also the position, we do something far simpler. It's simply we have the cell geometry, the direction was defined before, and we just calculate based on R epsilon the number of segments that we want to define on it, and we use that as the number of displacements that we use for the cell. Interesting fact is we sometimes have to encode the plane, but if we happen to have a number of quantization in terms of direction and in terms of displacement, which is 1 or lower, we actually have only one potential candidate for the plane. So we don't need to encode it. We know, and the decoder is able to know which is this plane. So we can just continue the encoding process without spending any bits. And as you might see, when we are in this case and we only have one candidate plane, we simply bisect the cell in its highest PCA direction in its middle, as you might see on the lower figure. Ordering. So as I presented before, we sometimes have a tree that is has a depth which is more important with our approach. The reason is we tend to optimize in terms of entropy. So we tend to have cells which are pretty empty and cells which are pretty full. So what happens is if we don't define an ordering, we might be bisecting cells which actually don't contain any point and don't bring any information for the point cloud reconstruction. To solve this problem, we define a very simple approach, very simple method based on the cell number of points and its geometry, which is simply the volume of the cell times the number of points. This will give a score, which will be used in the priority queue. The higher the volume and the number of points, the higher the error you will potentially made when you reconstruct the point cloud, and so the more important it is to bisect this cell. To represent it with the previous example, when we have this subdivision with few density, we will define such an ordering, like here. And when we have this, we know that S3, which has a higher score, will be the first one to be bisected. So the next planes that will be in the bit stream will be used to bisect S3. I will now present some results of our method. So introducing the distortion metrics that we use a two-sided Hausdorff and a PSNR method. So simply put, the two-sided Hausdorff we take from the reconstructed point cloud to the ground truth, the closest point distance. We do the same thing in the other direction. We add those two, and the PSNR is the following formula. So here are a few examples. So the first one with it's a Rhino. We can see how a method which is on the top is able to reconstruct the geometry pretty fast, even at very low bit rate. So from the left to the right on the right image, you can see low bit rate. So we send almost no data, and we have to still reconstruct a point cloud. And to the right when we have more data. From the curve, you might also see our solution in blue is able to reduce the distortion very fast, so with a very low bit rate. We have other examples. So here it's the Gustave Eiffel Nice Observatory. And as you might see, also, we tend to have less aliasing effect than other methods like the Villers-Grandon or Draco. And we tend to approximate geometry pretty well. Here is the last example with a dense object where we can clearly see that even on the our first reconstruction, we have captured the geometry. So I will present a progressive deconstruction example. So here is the Nice Observatory that we saw before with colors. And here is the compression. So on the right, you might see the rate distortion curve. The compression rate. So 1 over 1 million mean we compress the data 1 million times compared to the original. And we can see with this GIF how the more bits we send, so the lower the higher the rate, the more we approximate the geometry. Here is another example with the Rhino. And we can see we converge, even though we sometimes have a bit of noise, we tend to converge to the geometry at the end. So conclusion, we presented a compression method based on a BSP data structure. Our approach tends to approximate the geometry faster, though it requires far more work since we have to encode an additional information which is a plane. So we must encode at the same time the orientation and the displacement. We also have to define an ordering due to our entropy-based approach, which have an optimal in a non-equilibrated equal tree distribution. And we finally improve on the rate distortion from Draco and the Villers-Grandon, which are standard methods which are industry used. So thank you for your attention, and if you have any questions.
And stream triangle meshes. Like, why is your focus on point cloud instead of triangle meshes, where it would be like easier to have this sort of hierarchical applications?
So there is a lot of it's also industrial. There is a lot of industrial interest into point cloud. I mean, for multiple reasons, the scalability of the method, the proximity to the sensor. Since we are capturing point cloud with LIDAR, having a triangulation after it can introduce some mistake into the data. So we tend to work with point cloud since they don't introduce this kind of relative. We have, in fact, a lot of methods for 3D triangulation compression. Some were applied for point cloud compression. But the problem is with a 3D triangulation, you tend to send two information. You tend to send the point position, but also the triangulation. So it's a higher cost when you compare it to the point. That you can get back since you might have triangles that cover a lot of points. But it's a mix of industrial interest and sensor kind of observation.
One microphone up there.
Along this vein of discretizing more normals, I was wondering if you'd compared with KDOPs before.
Beg your pardon?
KDOP bounding hierarchies. So rather than just picking x-line plane, you pick a few different normal directions, and it's like you build a bunch of convex polygons, a hierarchy of convex polygons using a few discrete.
So you're speaking about this 3D direction sampling?
So like just like for x-line bounding class hierarchy, you would pick x, y, z as the three normal directions.
Yes.
And then interesting that people also will use a few other normal directions as well. Like so we pick like 6 different normals or 8 different normals. So we try to do something similar to what you're doing with Fibonacci, where
I see. I see. So we didn't experiment with this method. It's true that the interesting fact is a point cloud, industrial point cloud, might have some main direction depending on how it was built. And those directions might be really interesting, and it might help into reducing the bit rate, since we will have a quantization which is far lower. But unfortunately, we didn't experiment with that, since we also wanted to be able to represent free-form objects. And we might imagine that with free-form object, we don't have those kind of normals that appear very, very obviously. Thank you.
Hi. Thank you for the talk. So it seems that your plane-based subdivision of the space is able to effectively reconstruct the geometry of the original point cloud with few informations, which is fine. I was wondering how hard it could be to add additional information to the process, for example, colors attached to the points or textures or whatever else can be attached to the geometrical data.
Yes. This is a very interesting question, and it's in fact a big problem of point cloud compression. And usually the problem is not treated as one. It's often treated as two parts. So we have often geometry compression and color compression in another way. Some standard approach use a region adaptative hierarchical tree. So basically they represent, if you see a R transform, they use that on the color base once they have a tree, an octree, for example. But it's kind of rare to have the two problems that are treated as one. I think, in my opinion, the reason is because we are working on higher dimension. So it's the problem become less tractable, and it's also the geometry gives some information on the colorimetry. So using that as a prior to guess the color might be useful. A last point, which is also to note, is that color distortion is often less problematic for point cloud for industrial applications. So if you have more distortion on this, it's often more tolerated.
Okay, thanks.
So this concludes the session.